Hello everybody, welcome back to another geometry lesson. Today we're going to take a look at section 8.1. That's right folks, for this unit we are talking about similarity. How are two shapes similar to each other? So it would make sense to start talking about what it means to be similar. First of all, we say that two polygons are similar. Two polygons are similar, and we use this symbol here without the parentheses. It's called a tilde, and we use a tilde symbol to represent similarity. Two polygons are similar if they can transform into each other with a similarity transformation. Two polygons are similar if they can transform into each other with a similarity transformation. Okay, Mr. Schrager, so what's a similarity transformation? Well, I actually detailed what a similarity transformation is down below with this diagram. A similarity transformation preserves angle measures. So it's a transformation. Maybe we're rotating it or flipping it upside down or flipping it sideways that keeps the angle measures the exact same. So you'll see here that angle A is congruent to angle D, just like it says down here. The same can be said of angle B and angle C. Every angle is kept the same. But here's the catch. It's not the same triangle necessarily. You can make the triangle larger or smaller by multiplying all the values of your first triangle by some constant k. We call that our scale factor. So let's say, for instance, that a equals 3, and this mystery constant k is telling us that it is 2. What this is saying is, to get from the small shape to the large shape, we multiply the side lengths by 2. A times k equals ka. 3 times 2 is 6. So do we see how this side, doubled, makes 6? We can also go backwards. We can say that 6 divided by 2 is 3. So there are two parts to a similarity transformation, and we're going to write both of them down. A similarity transformation is a transformation that preserves angle measures and enlarges or reduces sides by a scale factor that we call k. Whenever you hear the word scale factor, we really want to think about what that means. In real life, you might hear someone say, this is a 1 to 40 scale factor of a train, or you scale by 3. Scaling just means multiplying by some number to make it larger or smaller. So let's take a look at the next page and see what we can do with this scale factor and with similarity. Here's the deal, everybody. I'm telling you right away with exercise 1 the following. I am telling you that we've got two triangles that are similar. Triangle RST is similar to triangle XYZ. This is just a statement of similarity. stating that these two triangles are similar. Our first question is to find the scale factor. Well, we know the scale factor is found by comparing the lengths of the sides. We can find the scale factor by asking ourselves, what do we have to multiply all the sides of the first triangle by to make our second triangle? We're also going to list all of our pairs of congruent angles and write the ratios of the side lengths in a statement of proportionality. There's a lot with this problem. Part 1 is going to be finding our scale factor. If you know that two triangles are similar, to find the scale factor, you should just divide the second triangle's side length by its corresponding side length on the first triangle. It's always going to be new divided by old to make the scale factor k. So, for instance, I could take this length here, xz. That's our new side length of 15, and divide it by rt. That's our old side length of 25. And what that'll do is it'll tell us how to get from the first triangle to the second triangle. Well, 15 over 25 is 3/5. So what this is saying is you could multiply any length in the first triangle by 3/5 and get a length in the second triangle. So 30 times 3/5 is 18, and 20 times 3/5 is 12. It matches up all the sides. That's part 1 of this problem. Part 2 is to list all congruent or pairs of congruent angles. Well, that one's easy. We've done it since Unit 5. We know that the pairs of congruent angles are any angles that are the same, and because all the angles in similar triangles are the same, we just have to match the letters. Angle R is going to be congruent to angle X, because they're in the same position in our triangle similarity statement. Angle S is congruent to angle Y for the same reason. You could also look down here and see that S and Y seem to be the same angle. And T is congruent to Z. So that's step 2, is writing the writing the pairs of congruent angles. The last thing we need to do, according to this problem, is to write the ratios of the corresponding side lengths in a statement of proportionality. A statement of proportionality sounds a lot crazier than it is, but it's very useful for us. A statement of proportionality lists each congruent side divided by its corresponding part. So, for instance, we know that xy divided by SR should also give us our scale factor of 3/5, right? So we could write xy over, RS. And it makes sense. X and Y are the first two letters of this triangle statement. R and S are the first two of this one. So it makes sense they would match up. We could do the same thing with YZ and ST. So we could say YZ over ST. We say that these two ratios are equal because 12 divided by 20 will be 3/5. 18 over 30 will be 3/5. And of course, when we did our purple line here, we already did ZX divided by TR. We know that ZX divided by TR is 3/5. So our statement of proportionality is just saying that no matter what side you divide, if you do the second side divided by the first corresponding side, you get 3/5. There's our statement of proportionality. Nice. For exercise 2, we are being told that the two polygons are similar. We have to find the values of x and y. Let's do part A together, and then we'll do B on our own. So for part A, we have two triangles here. We'll try and make it focus a bit better. There we go. And the idea is this. We already know what sides are going to correspond to what sides. Like, we know that this 21 is going to correspond to this 14. We know that this 18 is going to correspond with this 12. And we know that this unknown side, x, has to correspond with this known side of 20. The question is how to solve for x. And there's two ways to do it. The first way that I would recommend, and probably the easiest one for this section, is going to be to find the scale factor and apply the scale factor. So how do we find k? Well, to find the scale factor k, going from left to right, we take something in the second triangle and divide it by the corresponding part of the first one. I'm going to do 14 over 21. Since 14 is here, 21 is here, they're corresponding parts, we can divide them. 14 over 21 is 2/3. So here's what this tells us. This tells us that any side on this first triangle could be multiplied by 2/3 to make the second one. 21 times 2/3 is 14. 18 times 2/3 is 12. That also means that x times 2/3 is supposed to equal 20. So we can set up an equation. We could divide both sides by 2/3, but I'm going to be honest. Dividing by a fraction is almost never my thing. I hate doing it where I can avoid it. My recommendation is, instead of dividing by a fraction, we know that we can multiply by the reciprocal. Keep, change, flip. Let's go to cancel out on the left side, giving us x equals, and 20 times 3/2 is the same as 20 times 3 divided by 2. It's going to be 30. So that's the way I would recommend doing this. Another way you could do this problem is as follows. I'm going to do it on a separate sheet of... Actually, no, I'll do it right here. We have enough space. Another way to solve this problem is to set up something called a proportion. Remember our statement of proportionality and how it was a bunch of fractions equaling each other? Well, a proportion is just two fractions that equal each other. You do it by comparing something from one triangle to something of the other. So we could do, for instance, 14 over 21, just like how we found our scale factor, but then we want to compare another thing on the second triangle to another thing on the first. Let's compare 20 and x. So 14 over 21 equals 20 over x. We learned that we are allowed to cross multiply. This is something we did in middle school. So we do 21 times 20 equals 14 times x. 21 times 20 is 420. So 420 times or equals 14x. And we could just solve by dividing by 14. X equals 30. Same deal. So whichever method you use is up to you. With that said, I want you to try out part B. Keep in mind that we also have a missing angle here. So, take your time, try this problem out, pause the video, and unpause when you are ready. How do we do, folks? Let's start with how we found x. So, to find x, which was 7.5, we compared the sides we knew to the sides we didn't. We could either say the scale factor to go from 6 to 4 is 2/3, because 4 divided by 6 is 2/3. And then use that to say x times 2/3 should equal 5. Or we could set up a proportion. Either way, when we solve for x, we get 7.5. For the y variable, keep in mind that all quadrilaterals add up to 360 degrees. So the question remains, what angles can we compare? we know that all the angles for similar figures have to be exactly the same. They have to be congruent. So this 90 degrees has to match up with this 90 degrees. This 116 has to match up with this 116. This 61 should match up with this 61 based on the transformation that we're rotating at 180 degrees. So the question remains, what's missing? My recommendation is to set up an equation that equals 360. 360 should equal all of our sides added together. Because all of our sides add together to make 360, we can use this to solve for y. Nice. Let's flip back to the first page, because there are two more definitions I'd like to talk about. These ones are a bit trickier. To explain these definitions, I want you to draw the following. Across these two examples, I want you to draw a rectangle that looks like this, has the dimensions of 2 and 5, and I'd like you to draw another rectangle that looks like this, that has the dimensions of 15 and 6. My first question is it possible to find the perimeter of these two shapes? My second question is it possible to find the area? Well, let's start by finding the perimeter. I'm going to tell you right away that these shapes are rectangles. So actually, let me add in that these shapes are rectangles. If these two shapes are both rectangles, that means to find the perimeter, we add up all the sides. 2 plus 5, but don't forget that this side is 2 and this side is also 5. So 5 plus 5 is 10, 2 plus 2 is 14 units. We can do the same thing for the second rectangle. We can say that 15 plus 15 is 30, 6 plus 6 is 12, 30 plus 12 is 42 units. Now let's stop there for a second. What is the scale factor between these two rectangles? If I wanted to figure out how to go from this left rectangle to this right rectangle, I could do, for instance, 15 divided by 5, which is 3. So this is saying that we can multiply all the sides by 3 to get all the sides of the new rectangle. That means, just below, if I know the perimeter of the small rectangle, and I multiply it by 3, wouldn't I also get the perimeter of the large rectangle? It turns out that the perimeters of similar polygons are also scaled by the same scale factor that their sides are. If the sides can be multiplied by 3, the perimeters can be multiplied by 3. So this leads into the definition for perimeters of similar polygons. It goes like this. If two polygons are similar, then the ratio of their sides equals the ratio of their sides equals the ratio of their perimeters. These two ratios are the same, 3 and 3. Let's find the areas of these shapes. So if you recall, the area of a rectangle is base times height. So to find the area, we just multiply the base times the height. 5 times 2 is 10 units. But because we're talking area, we actually square our units. This is important. So 10 units squared is what we end up with. what's the area of the second one? Well, 6 times 15 is a bit tougher, but it does give us 90 square units. The problem is, if I go from 10 to 90, we might expect just be able to multiply by 3, like the scale factors. But 10 times 3 isn't 90. 10 times 9 is 90. So what happened here? Well, as area is often squared, we notice that our scale factor is also 3 squared, because 3 squared is 9. This gives us a really good rule to help us out here. When talking about the areas of similar polygons, you can find the areas by taking the scale factor squared and multiplying it by the original. So, for the areas of similar polygons, we say the following. If two polygons are similar, then the ratio of their sides squared equals the ratio of their areas. The ratio of their sides squared will equal the ratio of their areas. Let's see how we can use this. In exercise 3, your neighbor has decided to enlarge his garden. The garden is rectangular, with a width of 6 feet and a length of 15 feet. The new garden is going to be similar to the original, but it'll have a length of 35 feet instead. And we need to find the perimeters of both gardens. My suggestion for any of these word style problems, which you will be seeing quite a few of this unit, is to draw a diagram. So I'm going to draw the first rectangular garden with a width of 6 feet and a length of 15. And we know that the new garden is going to be just enlarged, but it is going to have a length of 35 feet. And somehow we need to find the perimeters of these. Well, finding the perimeter of the first one isn't a big deal. We know these are rectangular gardens, so can't we just add up all the different side lengths? 15 plus 15 is 30. 6 plus 6 is 42. So the perimeter is 42 feet. That's fine. But to find the new perimeter of the new garden, we would need to know what to multiply our old perimeter by. Since the perimeters of similar polygons are scaled up by the same amount, if we can find the scale factor of the sides, we'll know the scale factor for the perimeters. It'll be the same number we multiply by. Luckily, we are given two sides, a 35 and a 15. So we can do 35 divided by 15, and that'll be 7/3. So we can just multiply this by 7 over 3. 42 times 7/3 will give us the new perimeter. To do 42 times 7/3, I recommend taking 42, dividing it by the denominator 3, then multiplying the answer by 7. When we do, we will get 98 feet. Nice. Exercise 4 is super similar. In this diagram, we have two rectangles that are similar again, but this time we want to find the area of the larger polygon. Once again, I want you to pause the video here and see how we do with it. I want you to see if you can find the area of the larger polygon. Pause the video and come back when you're ready. How'd you do? Let's do this one together. So we know the area is going to be scaled here, but not by the scale factor. Rather, whatever the scale factor is, squared. So let's find the scale factor. To go from 3 feet to 6 feet, we do 6 divided by 3, and that gives us 2. So all the sides of this rectangle times 2 will make all the sides of this rectangle. That means the area times 2 squared, or 4, will equal the new area. And 27 times 4 is 108. Very nice. Next up, for exercise 5, we have the Mona Lisa, because obviously, right? So I recently found out the Mona Lisa is a lot smaller than people might realize. It's only 30 inches by 21 inches. I thought it took up like an entire wall. Famous art collector Herbert P. Sherbert has a scaled up version of the Mona Lisa, meaning it's bigger, at 50 inches by 33 inches. And we want to see if his version of the rectangular painting is to scale. In other words, we're trying to see if these two paintings are similar. So here's the original Mona Lisa in all of its glory. It's 30 inches on the side and 21 inches on this side. And we want to see if it is similar to Herbert's version, which is definitely much bigger. His version is 50 inches by 33 inches. So we need to figure out if this is similar or not. To determine if two shapes are similar, we first have to verify that all the angles are the same. But because I was told it was a rectangular painting, we know that all the angles are going to be right angles. We're fine with that. What I'm not fine with is knowing that all of our sides are scaled by the same scale factor. So let's calculate both of these scale factors. Since the new length is 50 and the old length was 30, we can do 50 over 30 to get 5/3. It seems like our scale factor should be 5/3 here. But when I do the same process with the 33-inch side and the 21-inch side, 33 over 21 actually simplifies to 11/7, not 5/3. So we would say, since the scales of each side are not proportional, meaning they share the same scale factor, the painting is not to scale. Not to scale. So there we go. These are not similar paintings, even if they look it. Last but not least, we need to decide if these two polygons are similar or not. And I want to remind you that to find if two polygons are similar or not, their sides should all be proportional, and their angles should all be congruent. Well, I'll give you the spoiler alert here, folks. Every side in the first polygon is proportional to the second. We can get 8 over 12 for these ones. We can get another 8 over 12 for these ones. We can get 6 over 9 for these ones. We can get, oops, I already used this color. We can get 4 over 6 for this. We can do 6 over 9 for this. No matter what, all the sides give us the ratio of 2/3. So we can at least say that all the sides are proportional. But there's another piece to shapes being congruent. I'm actually telling you that these shapes are not congruent because of one flaw. Only one of the angles is guaranteed to be congruent. Because as I'm looking at these angles, I am willing to put money on the fact that angle D, which looks to be about 135 degrees or so, does not match angle R, which looks almost flat. Those two angles are definitely not congruent. So we would say these two polygons are not necessarily similar because we don't know that the angles are congruent. Thank you so much for listening, everybody. I hope you have a fantastic rest of your day.